Let's go ahead and do an example problem. In this problem, we have a 3 millimeter rigid tank that contains hydrogen. The hydrogen is initially at 250 kPa and 550 Kelvin, and then the gas cools until the temperature hits 350 Kelvin. So the problem is asking us to find the final pressure and the amount of heat transfer. So in the first step, we're going to go ahead and we're going to draw a schematic. Right, it's a simple schematic with a tank that has hydrogen in it, and it's losing heat to the environment. Within that problem, we're going to go ahead and draw some assumptions. One assumption is that we're going to assume that hydrogen is an ideal gas. Right, and since we're assuming that hydrogen is an ideal gas, we're going to have to go ahead and assume that this ideal gas either has constant or variable specific heat. So what do I mean by that? What I mean is we're going to evaluate the heat transfer. Since we're evaluating the heat transfer of a system that contains an ideal gas, we're most likely going to have to look at the change in internal energy or the change in enthalpy of the ideal gas. For an ideal gas, the change in internal energy and enthalpy is a function of the specific heats. And when we evaluate the internal energy and or enthalpy of an ideal gas, it is a function of temperature only, and we have to go ahead and based on the fact that we have to take our specific heats into account, we assume one, that the specific heat is either variable or constant. What I mean by constant is that it is not a function of temperature, or it is a function of temperature. Right, so we're going to go ahead and do both. We're going to go ahead and solve this problem by doing a first law, assuming both constant specific heats and variable specific heats. So we're going to go ahead and do one or the other. So we're going to do it both ways just so that you guys can see the difference between how to evaluate this problem for both of those assumptions. Other assumptions that go with this is that the system is stationary. What I mean by stationary is that the system is not moving. Therefore, when we evaluate the change in energy of the system, we would equate the change in potential and kinetic energy of the system as 0. Also, we're going to assume that the system is closed, that there's no mass leaving or entering the system, which means that mass is constant. So with that, let's go ahead and let's go ahead and do part A. Part A is asking for the final pressure, right? So again, they give us the initial pressure, which is 250 kilopascals. They give us the initial temperature, which is 550 Kelvin. We're trying to find the final pressure, and they give us the final temperature of 350 Kelvin. Now, since this is an ideal gas, we can use the ideal gas law, basically equating that pressure times specific volume is equal to RT. With the ideal gas law, we can analyze this process from state 1 to state 2 by rearranging the ideal gas law and putting everything that's changing on the left-hand side of the equation, which is pressure and temperature, and putting everything that is not changing to the right-hand side of the equation. Therefore, that ratio is constant. So we get that the initial pressure over the initial temperature equals the final the initial pressure over the initial temperature equals the final pressure over the final temperature. We're given initial pressure, we're given initial temperature, we're given final temperature, and we can go ahead with this problem and directly solve for the final pressure. So that's part A of the problem. Part B of the problem is asking us to find the amount of heat transfer. So that would require first law analysis. And with the first law analysis, the first step is writing down the first law in its most compact form. E in minus E out equals delta E system. Now, E in is energy in by heat, mass, and work. E out is energy out by heat, mass, and work. And change in energy of the system is the total change of internal energy, plus the change in kinetic energy, plus the change in potential energy. There's no energy entering by heat, mass, or work, so that is 0. As far as energy out, the only energy leaving the system is heat. And since the system is stationary, the change in potential energy and the change in kinetic energy is 0, resulting in just delta U. So that means that I can go ahead and, since it is a closed system, mass is constant, therefore I can factor out the mass from the specific internal energy, and I can get it as U2 minus, or M times U2 minus U1. If I bring the minus sign to the other side of the equation, I get Q out is equal to mass times U1 minus U2. And then from this, I just need to find what my mass is, and I need to find my internal energy. Now the mass is pretty straightforward because since it's an ideal gas, I can write out the ideal gas law, pressure times volume equals mass times gas constant times temperature. If I use that equation and I rearrange it to solve for mass, I get pressure times volume over RT. I'm given that the volume of the tank is 3 cubic meters. I'm given the initial pressure. I'm given the initial temperature. And I can look up the gas constant in table A1. I can go ahead and I can solve for the mass, getting that I have 0.33 kilograms of hydrogen in my tank. Now, with that part solved, mass, all I need to do is now evaluate the change in internal energy of my system. Now, inside my system, I have an ideal gas. Therefore, I need to find the change in internal energy of an ideal gas. And if you notice, for an ideal gas, the internal energy is a function of temperature only. Internal energy is a function of temperature only, but that is only for an ideal gas. If this wasn't an ideal gas, you probably need two properties. Now, it just so happens that the change in internal energy for an ideal gas is the integral of CV, which is specific heat at constant volume, times temperature from T1 to T2. Now, this is where the two assumptions, variable specific heats or constant specific heats, come from. That is in how I evaluate this integral, right? If this is constant, that means this factors out of the integral, and the result of the integral is CV delta T. If it is not constant and variable with specific heat, I need to evaluate this integral. So we're going to go ahead and do this for both ways. First, starting with constant specific heats. So for assumption 1, we're going to assume that specific heat is not a function of temperature. That means constant specific heats. So that means my Q, which was originally mass times U1 minus U2. If I evaluate that integral, I end up getting mass times the specific heat, but some average specific heat, assuming it to be constant between the two temperatures, right? CV delta T, that's what that integral evaluates to. Now, how do I get a CV average? So if you go ahead and you turn to table A2B, you'll find that it gives you specific heat as a function of temperature for various gases. So if you go to that table and you find what the specific heat of hydrogen gas is, the specific heat constant volume at T1, and then you also find the specific volume of hydrogen at T2, and you take the average between those two temperatures, you'll find that the specific heat is 10.377 kilojoules per kilogram Kelvin. So with that value, you take that, you plug it into the equation here, and you end up getting a total heat transfer of 686.2 kilojoules. Now that's assuming constant specific heats. Let's go ahead and redo this for variable specific heats. So assumption number 2, we're going to assume that my specific heat is a function of temperature. Therefore, I need to actually evaluate that integral. Now, if you remember, I said that if you go ahead to the ideal gas tables, right? So the ideal gas table for hydrogen is table A22. So what we're trying to do is actually integrate the specific heat with temperature from T1 to T2. That means either evaluating the integral, or we can go to table A22A for the case of ideal gas. You'll notice that that is in molar quantities. We can find these values at table A22, and it accounts for the changing specific heat with, the changing internal energy with temperature and also accounts for the fact that my specific heat is variable with temperature. So basically, if I pull my numbers from these tables, it is as if I am integrating this. Right? So if you go to table 822, if you go to U1 is a temperature of 350 K. So if I look up the internal energy for hydrogen at 350 Kelvin, I need to interpolate. I get a value of 7,060.5 kilojoules per kilomole. I'm going to go ahead and call that U bar since that represents specific internal energy on a molar basis. And if I go ahead, I'm sorry, that should be U2, not U1. If I look at the value of U1, which is 550 Kelvin, I should find that my internal energy is 1,241 kilojoules per kilomole. Now, if you notice, I have mass here, kilograms, specific internal energy per kilomole, right? The units don't work out. So what I need to throw in here is I need to actually multiply this whole equation by 1 over the molarity. So if you go to table A1, and you look for hydrogen, you'll find that the molarity of hydrogen is 2.016 kilograms per kilomole. So knowing that I have my molarity, pulling the internal energy values per kilomole from table 822, knowing my mass, I can go ahead and I can put in those numbers and I can solve for Q and I get 685.8 kilojoules. So as you can see, the number is slightly different, right? I got 685.8 for variable specific heats, and I got 686.2 kilojoules for constant specific heats. Now, if my temperature difference between state 1 and state 2 was greater, you'd find that the resulting heat transfer calculation between variable specific heats and constant specific heats would be greater.